Hey everyone, this is Mr. K. Welcome back to Everything is Relative. Today we're going to be doing more topical past paper questions from the Papa Cambridge website for Cambridge A-level physics, and this time on the topic of oscillations. And I'm going to be looking specifically at questions 107 to 116 as they are numbered on the document from the website. I'll leave a link to the website in the description below, and you can use these questions, like always, as preparation for your exams, which are coming up soon. And these questions are slightly different from the questions we covered previously on oscillations, as they contain a little bit more about damping and resonance and so on. So I thought it was good to cover these concepts when talking about this topic of oscillations. And so the first question, again, this is a little bit blurry, is 107. The subject code is 9702. And this is from the summer 2020 exam. So that's May-June 2020, question paper 4, variant 2, and this is question number 4 from that paper. We are told that a dish is made from a section of a hollow glass sphere, and the dish, fixed to a horizontal table, contains a small solid ball of mass 45 grams, as shown in the figure, and the horizontal displacement of the ball from the center C of the dish is x. Initially, the ball is held at rest with distance x is equal to 3 centimeters. The ball is then released, and the variation with time of the horizontal displacement of the ball from point C is shown in the figure. So this ball is moving along this arc shape, along this curve shape, but we only really care about the horizontal displacement. And so we don't really have to care about the two-dimensional motion, but rather just the one-dimensional oscillation, which we can see is simple harmonic from looking at the graph. And indeed, the next question tells us that the motion of the ball in the dish is simple harmonic with its acceleration given by an expression a is minus g over r times x, where g is the acceleration of free fall and r is a constant that depends on the dimensions of the dish and the ball. And so we can see that this is simple harmonic, and we are asked to use figure 4.2 to show that the angular frequency omega of the oscillation of the ball in the dish is 2.9 radians per second. So am I given enough information? Well, I know that angular frequency omega can be written as 2 pi over the period of oscillation. And if I look at this graph quite carefully, I can find that the period of oscillation is 2.2 seconds. So if I start at the crest here and I look for the subsequent crest, and I do this accurately with my ruler, I can tell that that's 2.2 seconds. So one complete cycle takes 2.2 seconds to occur. And so omega, the angular frequency, is 2 pi divided by 2.2. And if I calculate this, what I get is 2.9 radians per second. Now, since they kind of told you what the value should be, the final answer, you aren't going to get an accuracy mark, so this question is only 1 mark. So when you see a 1 mark question, you can assume that it's going to be a straightforward calculation. Put in the equation that you know for the thing that you're trying to find, and usually that will work out quite simply. Now, however, we are told that we want to use the information in A to determine R. So R is a constant, but we don't really know what it is. Now, what we know is that the equation for simple harmonic motion, A is minus omega squared x. That means the thing in the bracket, g over r, is omega squared, because this ball is undergoing simple harmonic motion. So what I can do is equate omega squared to the thing in the brackets, which is g over r, which means then that r is equal to g over omega squared, and we can see that this is going to be the acceleration of free fall 9.81. Omega we've calculated, so we can just square this value. So in the denominator we have 2.9 squared, and we get, you'll notice that it has the units of meters, so it's actually like the radius of curvature of the dish, and we get 1.17 meters, or to two significant figures, 1.2 meters. So far so good, nothing really too difficult, out of the realm of what we understand when we study oscillations. We're then asked to calculate the speed of the ball as it passes over the center C of the dish. Aha, so now if I look at the diagram, what I know is that at the center C, at the equilibrium position, the object that's oscillating has the maximum velocity. It's the same for this ball. The ball's moving through C, it's moving at its fastest. If it's moving in the other direction, going up the surface of the dish, it's obviously slowing down. So the maximum speed is what we're trying to calculate the maximum speed. And we label the maximum speed V0. And what we know is that V0 is the amplitude x0 times the angular frequency omega. V0 is x0 omega, since V is x times omega. And the amplitude of x0, is 0.03 centimeters. Now, where do I get that value from? I can read it off from my graph. So it's either positive 3 or negative 3. The magnitude of that amplitude will be 3 centimeters. And so the ball doesn't go more than 3 centimeters horizontally. And then we multiply that by omega, which we calculated to be 2.9 radians per second. We get a speed of 8.7 times 10 to the minus 2 meters per second. And the question wants us to leave our answers in meters per second, so we can leave it as is. We don't have to write it as 0.0087. So we can write this as 8.7. I'm just going to leave it in scientific notation. 8.7 times 10 to the minus 2 meters per second, or rather 0.087. And so that's the speed, the maximum speed of the ball as it goes through or over the center C of the dish. It's moving fastest at that point. For part C, we are told that some moisture collects on the surface of the dish so that the motion of the ball now becomes lightly damped. And on the axis of 4.2, we are asked to draw a line to show the lightly damped motion of the ball for the first 5 seconds after the release of the ball. And this is a 3-mark question. So the most number of marks comes from a question where we simply have to draw what the graph would look like. We draw a line to show what the lightly damped motion of the ball would look like for simply the first 5 seconds. And there's a very specific instruction, only for the first 5 seconds. Now, they don't tell us how the ball is being damped, but they do tell us that it is being damped. So what I need to do is I need to draw light damping. Simple. I need to draw light damping, and how I draw it is up to me, but it must be consistent. So what I do is I just choose amplitude. And what I know about damping, when an object's motion is damped, each consecutive amplitude is less than the previous one. So subsequent amplitudes are lower than the previous amplitudes. And so I just choose at random points that are lower in amplitude, and I only need to go to 5 seconds, but I remember that my motion is still harmonic. It's not simple harmonic, but it's still harmonic. It still has a sine shape to it. And so what I would do, and this probably won't look as neat for me as it would for you, but you would draw this with a pencil, and you would make sure that you draw this as one complete line, and I would draw this something like this. And so you see the amplitudes will slowly decrease. Again, this is quite difficult to draw the way I'm doing it, but with a pencil it's a lot easier. And you have to make sure you aren't removing your pencil from the paper as you're doing this. You want one smooth line. It shouldn't look like there are any kinks in it. I think most importantly is the fact that every amplitude is less than the previous amplitude. So initially my amplitude was 2 less than the original amplitude, and then 4 blocks less, and then 6 blocks less, and then 8 blocks less. Again, there's no definite values, but this is light damping. Why? Because there are many oscillations happening. The object is not coming to rest immediately. It's undergoing many oscillations, so that's light damping. The fact that I have my amplitudes less than the old amplitudes, and the fact that my new graph is inside my old graph at all times, means that my graph is correct. So if you simply know what light damping is, you'll draw this graph in under a minute, neatly with pencil, and your understanding of the concept of light damping will help you score these 3 marks in very little time. So there isn't exact values that you need to plot. So you're essentially kind of sketching, more sketching a line rather than drawing it very accurately. But that's how you would draw or you would represent light damping if you were to do it on a graph, which is a common type of question. So you need to know how to draw it as well as be able to explain if you see a graph of light damping. Now the next question is question 108, and this comes from the summer of 2019 exam. It is question paper 4, variant 1, and this is question number 3 from that paper. We are told that a hollow tube sealed at one end has a cross-sectional area of 24 square centimeters. The tube contains sand, so the total mass m of the tube and sand is 0.23 kilograms, and the tube floats upright in a liquid of density rho, as shown in the figure. The depth of the bottom of the tube below the liquid surface is h. The tube is displaced vertically and then released, and the variation with time t of the depth h is shown in the figure. So basically what's happening is this tube is bobbing up and down in this liquid. And the variation in the distance below the surface of the liquid is shown. So h gets larger as the tube goes down and gets smaller as the tube gets closer to the surface. And this motion is simple harmonic. So although it looks confusing, I mean the idea is still the same. And we are asked to find the amplitude in meters of the oscillation. Now, how do we find the amplitude? Now, we have to be very careful. Firstly, the graph is giving us h in centimeters. Secondly, the equilibrium position is not the zero position. So the equilibrium position is h is equal to 4 in this case. So what I would possibly do, if I didn't want to get confused later on in the problem, is maybe draw a dashed line or a dotted line along that line, h is equal to 4. So now that's my equilibrium position. So the amplitude is my maximum value minus my minimum value divided by 2, or simply that distance. So I should say h naught, but I can still say x naught. It's okay if I change the symbols a bit, but the amplitude h naught would simply be 2 centimeters. And so I would write h naught, or I could write x naught, that's fine. 6 minus 2 divided by 2, 4 divided by 2, the last time I checked, is 2 centimeters. And to convert this to meters, I know that this is 2 times 10 to the minus 2 meters. Or again, I can write this as 0.020 meters, again to two significant figures. So not too bad, although the question seemed complicated, mathematically really wasn't that complicated. The next question asks us to find the frequency of the oscillation of the tube in the liquid. And now we can just apply our regular equations of simple harmonic motion. Looking at trying to find the frequency just as is might be a little difficult, so let me find the period first. So again, I like to use crest to crest. It's all up to you. It doesn't matter if you use peak or trough to trough. What I get is the time that it takes for two subsequent crests to appear, or to any 2 points in phase, is 0.6 seconds. So one complete cycle happens in 0.6 seconds. The pattern repeats itself every 0.6 seconds. And why do I need the period? Because frequency is 1 over the period, as we all already know. So that's 1 over 0.6, which is 1.67 hertz. I'm going to keep this to two significant figures, so the frequency is 1.7 hertz. Then we are told to find the acceleration of the tube when h is the maximum. So still, our regular equations of simple harmonic motion, a naught is equal to omega squared h naught. Again, I'm just looking for the magnitude of the acceleration, so I can ignore the sign here, because they didn't say when h is a maximum in which direction, so we're just expected to mention a magnitude. And I don't know the angular frequency omega, but I do know the frequency f. And what I remember is omega is 2 pi f. It's an equation I should never forget. So omega squared is 4 pi squared f squared times h naught. And all of these values are known. So that's 4 pi squared times the frequency 1.67 hertz squared times the amplitude 0.020 meters. And what we get is an acceleration of 2.2 meters per square second. Two significant figures. The acceleration is 2.2 meters per square second. We are then told that the frequency f of oscillation of the tube is given by this expression, 1 over 2 pi times the square root of a rho g over m, where g is the acceleration of freefall. And we are asked to calculate the density rho of the liquid in which the tube is floating. Now we can see that this question is 2 marks, so it shouldn't be too much of mathematics. Now what we know is that the frequency f is omega over 2 pi. Aha, that's starting to look a little bit like this expression above. What this means is that omega squared, so everything in brackets is the square root of omega. And so, or everything in brackets is equal to omega rather. And so omega squared is everything in brackets without the square root side. So omega squared is a rho g over m. Aha, so a little bit of a trick there, meaning I can rearrange this equation and solve for the density rho, rho being omega squared m divided by a times g. And again, all of these values are known. So omega squared is 4 pi f squared, that's 4 pi squared times the frequency 1.67 hertz squared times the mass, which we are told the sand in the tube is 0.23 kilograms, divided by the area. The area we are told is 24 square centimeters, which is 24 times 10 to the minus 4 square meters. Remember, you must convert to meters. And multiplied by g, which is 9.81 meters per square second. And we get the density of the liquid to be 1.1 times 10 to the power 3 kilograms per cubic meter, or 1,100 kilograms per cubic meter. And so when you see an expression like this, don't be afraid, go to your expressions for omega and f. If there's any complicated variables in a bracket that you've never seen before, think of your equation for simple harmonic motion, and then think of your equations that relate f to omega if you need them. And then you can simplify and solve for any of the variables that you haven't seen before. Now the last sub-question, part C, says the oscillations illustrated in figure 3.2 are undamped, but in practice the liquid does cause light damping. And on figure 3.2 we have to draw a line showing light damping of the oscillations from t is equal to 0 to t is equal to 1.4 seconds. So again, they don't really give us any other constraints of the light damping, besides the fact that it needs to go from 0 all the way up until 1.4 seconds. So basically your light damping needs to cover the entire graph sheet. And so again, these lines I drew them for myself. You didn't need them, but I just drew them. But now I really need to draw the graph of light damping. And I'm basically going to do what I did before. Every amplitude, like I did in the previous question, every amplitude is less than the one before it. And so what I end up with is a harmonic sinusoidal function that is decreasing in amplitude with every oscillation. And so it'll start at the maximum. And then again, remember, this will be much neater if I were to do it in pencil. And it needs to look like a curve. It can't look like straight lines with pointy edges. It needs to look like it actually is a curved harmonic function. And it must have an amplitude that's decreasing. as such. So it would have a similar shape. It would have the same period or a period that's slightly longer. Remember, when there's damping occurring, the period can be slightly longer. I prefer to keep the period the same because then it's easier to draw the shape. So either or would be allowed, as you can see in the mark scheme. If you were to look at the mark scheme, either or would be allowed, but I prefer to keep the period the same so that it's easier to sketch what this graph would look like. So it looks like a sine graph that's being compressed after each cycle, which essentially it is. There are many oscillations, so it is indeed light damping. If there was only one oscillation and then nothing, that would be heavy damping. And so you need to be able to identify damping, but you also need to be able to sketch damping if asked. Particularly light damping, but they could ask you to sketch critical or heavy damping as well. And so that question was 10 marks altogether. Interesting question and fairly long. I think the graph drawing will determine how long it takes you to answer a question like that. Now the next question is question 110. This is question 110. This comes from the winter 2019 exam. So November, December. It's question paper 4, variant 2, and it's question number 4 from that exam. Something slightly different, we are told that a ball of mass m is held on a horizontal surface by two identical extended springs, as shown in the figure. One spring is attached to a fixed point, whilst the other spring is attached to an oscillator. The oscillator is switched off, so essentially there's two fixed points with springs attaching to the ball, and the ball is displaced sideways along the axis of the springs and is then released. The variation with time t of the displacement x of the ball is shown. So it looks simple harmonic, but we see the amplitudes are compressed after each cycle. So immediately we know there's damping happening here. We aren't told that there's damping happening, but the graph is telling me that there's damping occurring. And you can see the first question asks me to state what is meant by damping. Well, kind of a few ways you can answer this kind of question, but what is damping? Well, damping is when the amplitude of an oscillating system is reduced because the energy is reduced. But simply, damping is the loss of energy of any oscillating system or an oscillating object, whichever you prefer. So the mark scheme says the loss of energy, but I think more specifically damping is when an oscillating system loses energy, because we are talking about oscillations. And we then want to state the evidence provided by figure 4.2 that the motion of the ball is damped. Well, you could probably talk about the periods expanding slightly, but I think most importantly, how do I know that these oscillations are damped? Well, I can simply see the amplitudes are decreasing with time. And I don't have to go to explain any further. Damping, as we learned it, occurs when the amplitude of the displacement, or just the amplitude, decreases with time. And we could go one further and ask what type of damping this is, and we can see clearly that this is light damping, because there are many oscillations. The object still oscillates, but with a lower amplitude each time. We are then told that the acceleration a and the displacement x of the ball are related by an expression. A is minus 2k over m times x, where k is the spring constant of one of the springs, and the mass m of the ball is 1.2 kgs. And we want to use data from the figure to determine the angular frequency of oscillations of the ball. So don't be worried, although this is not simple harmonic motion, there's still a period to this motion, a constant period. And if I look for this period, what I find is that this period is 0.8 seconds. So again, I'm going to go crest to crest. They may not be at the same height, but it's still two subsequent points of where the maximum displacement is occurring. And so that period is 0.8 seconds, meaning omega, the angular frequency, is 2 pi over the period, which is 2 pi over 0.8, and this gives us 7.85 radians per second, or to two significant figures, 7.9 radians per second. So I can still find the period even though it's not simple harmonic. We're then told to use the answer in 1 to determine the value of k. Now where's k? K is in the brackets again. A is equal to minus something times x. We know from the equation for simple harmonic motion that a something is omega squared. And so omega squared is equal to 2k over m, which means that we can rearrange and solve for k. K is omega squared m divided by 2. Omega, I know, 7.85 radians per second squared. The mass, I'm told, is 1.2 kgs divided by 2. And what I get is k. Remember, k, they told us what it actually is. It's a spring constant. And so I know if all my values are in SI units, it will have a unit of Newton per meter. So it's 37.0 newtons per meter. Or again, the two significant figures, 37 newtons per meter. And you'd think that the question ends there, but it doesn't actually. So the question actually continues. And part C says the oscillator is switched on. So in terms of real estate, this question is quite long. It occupies quite a bit of pages in this paper. The oscillator is switched on, and the amplitude of oscillation of the oscillator is constant. The angular frequency is gradually increased from 0.7 omega to 1.3 omega, where omega is the angular frequency we calculated. On the axis of figure 4.3, we want to show the variation with angular frequency of the amplitude A of the oscillation of the ball. So immediately, what do we know? I need to plot a graph of amplitude versus frequency. Now, there is only one graph of amplitude versus frequency that we actually know, and that's the graph for resonance. So what's going to happen is when I move the oscillator and I change the frequency of the oscillator from 0.7 omega to 1.3 omega, at some point I'm going to get resonance happening where the frequency of the oscillator is going to match the natural frequency of the mass oscillating on the springs. But how do I know what the natural frequency is? Well, the natural frequency is the frequency we calculated. We displaced the ball a slight distance, and we got a natural frequency of 7.9 radians per second, or an angular frequency, which is similar to a frequency. And so I get the maximum amplitude at omega. And so what I have is my typical graph of resonance. So at lower frequencies, I don't get a maximum amplitude. But as I reach the maximum amplitude, I have a very sharp peak. As I reach the natural frequency, rather, I have a very sharp peak of an amplitude. The maximum amplitude happens when the natural frequency matches the driving frequency of the oscillator. And then at any higher frequencies, the amplitude drops again. And so this is just like the effect that you would have seen when you were studying the topic of the subtopic of resonance. But when the oscillation of the oscillator has a frequency that's the same as the natural frequency of the mass that's vibrating, then we have the maximum amplitude. So the simple sketch would look like this. It must have a sharp peak at omega, it must be lower, and it must be a curve. It must increase to the maximum amplitude of 1 omega and then decrease afterwards. We're then told that some sand is now sprinkled on the horizontal surface, and the angular frequency of the oscillations is again gradually increased from 0.7 omega to 1.3 omega. And we want to state two changes that occur to the line that you have drawn on figure 4.3. Aha. So exactly the same scenario, but I now sprinkle some sand on the surface on which the ball is oscillating. So I'm still having resonance occurring, but I'm adding friction. So what does friction do? Friction removes energy. What do we say when energy is removed? Damping happens. So you have to now remember the graph of damping for what happens to damping when you have a graph of amplitude versus angular frequency. And essentially what happens is the graphs have a lower peak, and the peak is shifted slightly. I'm not really going to draw them here, but the peaks are shifted very slightly to the right. Red being critical damping, or and green being heavy damping, if you would. And so the heavier the damping, the lower the amplitude would be. That's to lower the energy, right? We damp systems, we don't want to have a high amplitude of oscillation, like bridges and buildings and so on. So what two changes will occur to the line specifically? Specifically, they want to know how the line look different. So the first thing I'm going to say is there is a lower peak. There's a lower peak. I think it's not a completely well explained what peak would mean. I guess it's fine actually. Or lower max value for A. So I can say there's a lower peak or lower maximum value for A. So the amplitude will have a lower maximum when there's damping occurring. And that's good because it prevents our bridge from collapsing or a building from falling over in heavy winds and so on. Anything else that will happen? Well, I'm thinking that the peak will also be less sharp. So the maximum value is more flat. As you saw in the graphs that I drew, they are more flat and they are more tilted slightly towards the right. So you can say they're less sharp or you can say they are more flat. So this, well, believe it or not, this is a sharp peak, but any other peaks for damping would be much smoother. So there's a higher range of frequencies that will give a closer to maximum amplitude as we increase the amount of damping. And so that question was 10 marks, and this was significantly long in terms of the amount of words that you had to read, which will significantly impact how long it takes to answer the question. But if you look at it at the surface, everything is based on concepts that we already understand, was just set out in a very long, sort of cumbersome way. So it's very important to be efficient as well as effective when answering these kinds of questions. The next question is question 111. It's 9702, not 9720. It's subject code for A-level physics. And this comes from the March 2018 exam. Question paper 4, variant 2, and this is question number 4 from this paper. And this question starts off by saying, explain what is meant by the natural frequency of vibration of a system. Now, the natural frequency of the vibration of any system is the frequency at which the system will vibrate if there's no external forces or driving forces acting on it. So we can write it just as is. It's the frequency at which a system will vibrate. So quite a long answer for a 1-mark question. Will vibrate in the absence, or if there isn't a driving force acting on it, but I like to say in the absence of a driving force acting on it. So if I pluck a guitar string and I let it go, there isn't a driving force. I've allowed it to vibrate at its natural frequency when I've left the guitar string. And so it will vibrate at its natural frequency, the frequency at which a system will vibrate in the absence of a driving force. That is natural frequency of system. We're then told that a block of metal is fixed to one end of a vertical spring and the other end is attached to an oscillator as shown. Again, this oscillator is something that can move, but initially it's fixed. The amplitude of oscillation of the oscillator is constant, and the variation of the amplitude of the oscillations of the block with the frequency f of the oscillations is shown. So you can see amplitude increases as frequency increases, and then there's a peak, and after that point the frequency decreases, or rather the amplitude decreases with frequency. So clearly we can see, and going from the questions that we've already done, that this effect is resonance. We don't really need to explain why, but you can see that when amplitude changes with frequency, that effect is resonance. And so when amplitude changes with frequency, the effect that we have is called resonance. Name the effect shown in the figure. Remember, this kind of graph, if you look at it, you can immediately state what type of effect it is. And x0 here is amplitude. So that's so they could use the symbol A, but you could also use the symbol x0 for amplitude. And we want to state and explain whether the block is undergoing damped oscillations. So how do we know if the oscillations are damped at all? Well, essentially, if we don't damp oscillations, then when you provide energy with an oscillator, the peak amplitude will be infinity, because the oscillator continues providing energy, and so the thing that's oscillating, in this case the metal block, will continue to have an amplitude that will go to maximum. But there will be some damping from internal components of the spring, from friction, from air resistance, whatever they may be, there will be some damping. And so what we can say to explain that is that the peak is not an infinite height. So the fact that the peak is some finite value means there's some damping occurring. It may not be significant damping, but we can simply say the peak is not an infinite height, or the maximum value, the maximum amplitude is not infinity. And so that tells us, that's enough to tell us that the oscillations are damped. We can also say that the peak is not very sharp. We could say that the peak is more smooth or flat or rounded at the top rather than being quite sharp. But it's hard to tell in this figure. So I think it's safer to say that the peak is not an infinite height, so oscillations are damped. And the last question says, state one example in which the effect in figure 4.2 is useful. So when is resonance useful? So you may not have studied the MRI, but an MRI is one case where resonance is useful, magnetic resonance imaging. Ultrasound is something that you would have studied, and ultrasound does require resonance, requires the crystal to vibrate with its resonant frequency. The driving frequency needs to be of the potential difference, needs to match the natural frequency of the crystal, so we get greater amplitude of waves going into the body. Microwave ovens have use resonance as well to make sure the energy of the microwaves are high, they have high amplitudes. And the crystal, the quartz crystals that we use in analog watches, also vibrate with resonance to make the effect more pronounced and make sure that our timing is correct. And so these are some examples, but there might be others. They only asked for one. I've just given you a few. You can choose any one of these. So this was a more shorter question and not any mathematics at all, really. Purely conceptual. Short question, 5 marks, but mostly based on damping and resonance. So you need to know damping and resonance as much as you need to know simple harmonic motion. The next question is question number 112. And this comes from the summer 2018 exam. This is question paper 4, variant 2, and this is question number 4 from that exam paper. We are told to state 2 conditions necessary for a mass to be undergoing simple harmonic motion. We know this very well now, that for simple harmonic motion, the acceleration is proportional to the displacement, and I'm going to say from a fixed point to be more concise. So the acceleration is proportional to the displacement from a fixed point, or from the equilibrium position is fine. And the second condition is there's a minus sign in the equation. And this means that the acceleration and displacement are in opposite directions to each other. Or simply saying acceleration and displacement are in opposite directions is perfectly fine. So those are the 2 conditions that we need for simple harmonic motion. And the equation for simple harmonic motion, the acceleration equation, tells us this. We're now told that a trolley of mass 950 grams is held on a horizontal surface by the means of 2 springs attached to fixed points P and Q, as shown in the figure. We're probably tired of these types of questions now, but it's good that we get practice. The springs each have a spring constant of 230 newtons per meter and are always extended. The trolley is displaced along the line of the springs and then released, and the variation with time of the displacement of the trolley is shown. So we can see something is happening. We can see that this is harmonic, but it's losing energy, so it's not simple harmonic. It's close to simple harmonic, but it's being damped very, very slightly, losing energy. And this kind of answers my first question. The first question says, state and explain whether the oscillations of the trolley are heavily damped, critically damped, or lightly damped. Well, I can see that the oscillations keep going, and the amplitude only drops very slightly after each subsequent oscillation. So what I can say is that there's a small change in amplitude between, I'm doing the explanation before I actually give the answer. The small change in amplitude between oscillations tells us that it is lightly damped, or this represents light damping. So a very small change in amplitude between oscillations, as we can see the amplitude is there, and then for the next oscillation it's not much less, and then for the next oscillation it's not much less, and this will continue for a while before it eventually comes to rest. We're then told to suggest the cause of the damping. Well, the first thing that comes to mind is that damping is the loss of energy. What will cause this cart to lose energy? We could speak about friction between the springs in the wall, or energy being lost in the springs themselves in the form of heat, but I think the first thing that comes to mind is the simplest one, and that's friction between the wheels of the cart and the surface. And we'll say specifically what this does. It causes the trolley to lose energy, which is us kind of explaining damping in a way. So the friction between the wheels and the surface causes the trolley to lose energy. Or you can say it any other way that you think the trolley may be losing energy, air resistance and so on. The acceleration of the trolley of mass m, the acceleration a of mass m, may be assumed to be given by a is minus 2k over m times x, equation we've actually seen before. We are asked to calculate the angular frequency omega of the oscillations of the trolley. And what we need to do is, omega is 2 pi over t. Hooray, and we go to our graph and we get the t. Aha, we're in trouble. We aren't given values for the time. So we can't use our trusted equation to find omega. But what we can do is say omega squared is the thing in brackets, 2k over m, since a is minus omega squared x, which means that omega is the square root of 2k over m, which is the square root, and I'm given the value for k. They told us that k, the spring constants, were 230 newtons per meter, over the mass, which they also gave us, 0.95 kilograms, which means we can calculate omega, and we get it to be 22 radians per second. Two significant figures, 22 radians per second. We're then asked to determine the time t1 shown in the figure. So here's where it can get a little bit complicated. I need to calculate this time t1. And so how am I going to figure out what t1 is? Well, for me to find any time is going to be quite difficult. But there is a time that I can find that is related to the thing I calculated, the omega. But that's the period. So what I can do is try to figure out what t1 is in terms of the period. How many periods is the time t1? So what I have from here to here is one period. What I have from there to there is not one period, but it's half a period, because my second period would be somewhere there. And so what I have is 1.5 periods. So the value of t1 is related to the period. And t1 is 3 over 2 periods, or 3t over 2, which is 3 over 2, and t is 2 pi over omega, since omega is 2 pi over t. So it's 3 over 2, not equal to, but multiplied by 2 pi over omega. I can now calculate this value for t1. So I had to do a little bit of mathematical manipulation there. So it's 3 over 2 times 2 pi divided by 22. And this gives me a time of 0.5 4 to 8 seconds, or to two significant figures, 0.43 seconds. So even though there were no times given, I could use the fact that I knew omega, and then also use the fact that I could find T1 in relation to the period, and then calculate T1 because I know what the period is, or I could calculate the period since I have omega. And so a little bit of extra steps, but doesn't change the fact that we know what we know. So never doubt yourself when you see a question like that. Now the next question is question 114. And this is from the winter 2018 exam. This is question paper 4, variant 2, question 4 from that paper. Also a fairly common question, I've seen it a few times actually. A U-tube contains liquid, as shown in the figure. The total length of the liquid in the column is L, and the column of liquid is displaced so that the change in height of the liquid level from the equilibrium position in each arm is X, as we can see in the figure. So that equilibrium position is the middle line, and the liquid oscillates up and down from that equilibrium position, just like any other object undergoes simple harmonic motion. The liquid in the U-tube then oscillates such that the acceleration A is given by A is minus 2g over L times x, where g is the acceleration of free fall, and we want to show that the liquid column undergoes simple harmonic motion. So basically we want to show that A is equal to minus some positive constant, because omega squared always will be positive, times x. So what I can see is immediately g is an acceleration, it's always greater than 0. L is also a positive constant, it's a length, it's always greater than 0. And so what this means is the acceleration is proportional to minus x. So proportional to x, but also proportional to minus x. So A is equal to minus kx, where k is some positive value. And what do I know? This is the defining equation for simple harmonic motion. And so immediately that's enough. I would think that's enough, but I need to also say that G and L are constants. So just like omega is a constant, G and L must be constant because they're inside the bracket. So I must specifically say that G and L are constants, and must conclude that the defining equation is in fact held by saying that A is proportional to x and in the opposite direction to x. So you want A to be proportional to x because G and L are constants, in the opposite direction because since they're both positive, the minus sign means that A and x will always be in opposite directions. And so you could do a little bit more working than is required there, but again, rather be safe than sorry when answering a question like that. Next, we are told that the variation with time t of the displacement x is shown. We can see again, harmonic, not simple harmonic, because the amplitudes are decreasing with time, but they're decreasing not very rapidly. And we are asked to use the data from the figure to determine the length of the liquid column. So immediately I go, and I know that omega squared is the thing in brackets, 2g over L. And what I also know is that omega squared is 4 pi squared over t squared, since omega is 2 pi over t. Now I don't know omega, they didn't ask me to calculate like I did in some previous questions, so I need to find t before I can find L. So you know I like to do my algebra first and then rearrange the equations before putting in values. But if I turn this around, I can solve for L, and I get L is 2g t squared divided by 4 pi squared. So that's 2 times 9.81. Now yes, I don't have the period, but I also can find the period. And if I go to this graph, I can see that the period from crest to crest to subsequent points in phase, I have the period is half a second. The time is being measured in seconds, 0.5 seconds. So that's 0.5 squared divided by 4 pi squared. And what I get is 1.24 times 10 to the minus 1 in meters. And so this length in two significant figures is 0.12 meters. So that's the total length of the liquid column. I didn't need to do any fancy mathematics because the equation for the defining equation for simple harmonic motion in this case was already given. We're then told that the oscillations in figure 4.3 are damped, and we want to suggest one cause of the damping. Well, we can see that the oscillations are damped because of the figure itself. They could have asked us to explain if it was damped or not. But what is one cause of the damping? Now, there are many different options here. This is not a ball on a track, but there can still be friction. There can be friction within the liquid. There can be friction between the liquid and the tube, and there could be things like viscosity and so on, and drag, viscous drag, and whatever. But again, I like to think of the simplest ones because, well, it takes less time to think of the simplest ones. And I'm just going to say friction between the liquid and the tube. And that will be a significant amount of friction between the liquid and the tube, which will cause the damping. Next, we are told to calculate the ratio of the total energy after 1.5 complete oscillations over the total initial energy of the oscillations. Aha! So first one of these kinds of questions. Let me first remind myself how energy and amplitudes are related. Well, let me just write an equation for energy. I know that total energy is a half m omega squared x naught squared. So maybe check out the crash course that I do on oscillations to understand where this equation comes from. But what it means, if I'm keeping m and omega constant, which I am, I'm not changing the mass, nor am I changing the angular frequency because the period is not changing, then the energy of the oscillations is directly proportional to the square of the amplitudes. Aha! So that means that if I were to take the new energy, the energy after 1.5 oscillations divided by the initial energy, E old, what I'll get is that those constants half m omega disappear, and I get that this will be equal to the new amplitude squared divided by the old amplitude squared, or simply new amplitude divided by old amplitude all squared, which is easier to do. And the new amplitude, after they asked for 1.5 complete oscillations, so one oscillation and then another oscillation, I'm looking at, so that's 1 and that's a half. So I'm right here, and what I get is this value is 1.3 centimeters. And so the new amplitude is 1.3 centimeters divided by the initial energy, the initial amplitude rather. The initial amplitude is 2 centimeters. So I'm going to divide that by 2 centimeters and then square. I don't have to convert to meters because the conversions wouldn't make a difference since we're taking the ratio. And what I get is a ratio that is 4.23 times 10 to the minus 1, or 0.42. Again, your ratios must always be in decimal, must be a decimal number. We need to know the number of significant figures. It's a value. It's a calculated value. So 0.42 to two significant figures. So 42% of the energy is lost after simply 1.5 oscillations. It's not a very good system to study simple harmonic motion because although it's a light damping, it's still damping and there's still energy lost at fairly rapid rate. And so the ratio is 0.42. So whenever you're asked to calculate the ratio of energies, look for the amplitudes. And the squares of the amplitudes will relate to the energies. And so that was a 8-mark question. And the first time we saw a question there on comparing the energies at different times. The next question is actually very similar. You can see it was created for the exam happening at around the same time, so they changed the question very slightly. It's the winter 2018 exam. And this is question paper 4, variant 3, question number 3 from that paper. Again, we have a U-tube containing a liquid. The total length of the column of liquid is L, and the column of liquid is displaced so that the change in height of the liquid of each arm is x, as before. The liquid in the U-tube then oscillates with simple harmonic motion such that the acceleration A is given by minus 2g over L times x, where g is again the acceleration of free fall. And this time we are asked to calculate the period of the oscillation when the length is 19 centimeters. Well, what I can tell is that A is minus omega squared x, which means that omega, I want the period, omega is 2 pi over t. Actually, don't even need omega squared is 2g over L. And now I can say omega is 2 pi over t, so omega squared is 4 pi squared over t squared, which is equal to 2g over L, the thing in brackets. Which means that the period t, if I do some mathemagic here, is the square root of 4 pi squared L over 2g, which is, if I put in my values, the square root of 4 pi squared times 0.19 divided by 2 times 9.81. And this gives me a period of 0.618 seconds, or to two significant figures, 0.62 seconds. So I had to first equate omega squared to the thing in brackets, 2g over L, and then remember that omega is 2 pi over t. And so there will be marks awarded for everything that you remembered to do for that problem. A very similar graph is shown again. The variation with time t of the displacement is shown. And the period of oscillation of the liquid column of mass 18 grams is t. And the oscillations are damped. And again, they're asking us for one cause of the damping. So like I stated before, there could be friction, viscous drag, air resistance, whatever. Well, air resistance not so much, but mostly I would think the best thing or the simplest thing to think of in the heat of the moment is the friction between the liquid and the tube. So there's viscous drag, there's friction in the liquid itself, but simply the friction between the liquid and the tube is good enough because they only asked us for one cause of the damping. Now, in the next question, they ask us very specifically to calculate the loss in total energy of the oscillations during the first 2.5 periods of the oscillations. So they're not asking us to calculate the ratio, but the loss. So what I need is the initial energy minus the energy after 2.5 periods have passed. And I tell you what, if I remember my equation from energy, equation for energy rather, E is equal to a half m omega squared x naught squared. I'm going to need omega somewhere here, and I haven't calculated it. So since I have the period, I'll just do an aside working to calculate omega. So omega is 2 pi over t. I don't usually do this. I like to do my workings, my algebra in the calculation, but since this is a little bit of a messy calculation, I can do it aside. So that's 2 pi over 0.618 seconds, which we calculated for the period, which is 10.2 radians per second. So now I'm going to have to write the energy equation for the initial energy equation and then the equation for the energy after 2.5 periods. So that's a half times the mass remains constant, omega remains constant, omega squared remains constant. The amplitude for a 0 period squared minus the energy after 2.5 periods is a half m omega squared, and the amplitude now changes after 2.5 periods squared. So I need the mass and omegas. They don't cancel in this case because I'm not calculating a ratio, but rather a difference. And so this is half times the mass, which is 18 grams, so 18 times 10 to the minus 3 kg, times omega squared, 10.2 radians per second squared, into, now what's the original amplitude? When period is 0, the amplitude is 2 centimeters. And I also have to convert this 2 centimeters to meters. So that's 2 times 10 to the minus 2 squared minus, what's the amplitude after 2.5 periods? Well, the amplitude after 2.5 periods is there. It's just less than 1. It's actually 0.95. Again, I only need the magnitudes of the amplitudes. Don't need the actual signs. 0.95 times 10 to the minus 2 meters squared. And what I get is the difference in energy being 2.90 times 10 to the minus 4 joules. Or to two significant figures, 2.9 times 10 to the minus 4 joules. So energy-wise, at least joules-wise, not a lot of energy is lost in the first 2.5 periods of the oscillations. Ratio-wise, it might be a different story, but the actual amount of energy is not that significant. But then again, to think of this liquid column oscillating, there wouldn't be that much energy to begin with. And so that's how you would calculate the loss in energy as opposed to the ratio of energy. So just be careful and always read the question carefully to make sure that you are answering what is asked of you and nothing else. The last question here is question 116. And this question comes from the summer of 2017. It's question paper 4, variant 1, and it's question number 2 from that paper. We're told that a bar magnet of mass 180 grams is suspended from the free end of a spring as shown in the figure. The magnet hangs so that one pole is near the center of a coil of wire. The coil is connected in series with a resistor and switch. The switch is open. The magnet is displaced vertically and then allowed to oscillate with one more pole remaining inside the coil. The other pole remains outside the coil. At time t is equal to 0, the magnet is oscillating freely as it passes through its equilibrium position. And at time t is equal to 3 seconds, the switch in the circuit is closed. Now the variation with time t of the vertical displacement y of the magnet is shown in the figure. So we can see that once the switch is closed in the circuit and there's a current passing through the coil, the magnet starts to get damped. So simply put, we aren't studying magnetic fields here, but we can see that the magnetic field of the magnet is interacting with the magnetic field of the current produced in the coil. And so the current produced in the coil is producing a magnetic field that is opposing the field of the magnet and hence damping the oscillations. And you can see the oscillations damp after the first 3 seconds. We are then told to determine two significant figures the frequency of oscillation of the magnet. Well, the frequency is easy. It's 1 over the period. And the period I can determine simply by looking at the graph. So the period would be, if I see it correctly, 1.2 seconds. So frequency is 1 over t, which is 1 over 1.2, which is 0.8833 hertz. So you can see they brought in a little bit of magnetic fields into this question. You need to know your topics all together, and you need to be able to answer questions that combine multiple topics. So the frequency is 0.83 hertz. Now we also want to state if the closing of the switch gives rise to light, heavy, or critical damping, and I think you will agree, again, this is light damping. Many oscillations, not a massive change in amplitude for each subsequent oscillation. But they only want to know what type of damping it is. They don't ask for a reason. So we can simply say it is light damping. And the next question, similar to the previous question that we had, the last sub-question of the previous question, says calculate the change in energy delta E of the oscillation of the magnet between 2.7 seconds and 7.5 seconds. And we want to explain our working. So delta E is equal to the energy at 2.7 seconds minus the energy at 7.5 seconds. Now what I remember is that energy is proportional to the square of the amplitude. So as part of my explanation, what I'm going to do is simply write down everything I'm thinking. So when you're asked to explain, it's good to always put your points in as you're thinking of them rather than doing things in your head. So the amplitude at, I'll just write it at 2.7 seconds is 1.5 centimeters. So I can write in centimeters, I'll do the conversions later on. And the amplitude at 7.5 centimeters, so it's basically me doing 7.5 seconds rather, is 0.75 centimeters. And so that's me sort of doing an explanation. But again, when I'm asked to explain, I should always write down what I'm thinking. And then mathematically, I know that this is a half m omega squared. Now I multiply all of this by the difference in the squares of the amplitudes. So that's x naught at 2.7 seconds squared minus the amplitude x naught at 7.5 seconds squared. And I have all of these values. I know m, I know omega. And so this is a half times the mass, which they told us is 0.18 kilograms. I don't know omega, but I do know the frequency, and omega is 2 pi f. So that omega squared is 4 pi squared times the frequency squared, 0.833 squared, into, now I'm going to convert the centimeters into meters, so that's 0.015 meters squared minus 0.0075 meters squared. And so what I get is that the difference in energy between 2.7 and 7.5 seconds is 4.16 times 10 to the minus 4 joules. In two significant figures, this is 4.2 times 10 to the minus 4 joules. So that was a significantly long question. Generally might be worth 4 marks, maybe 5 marks, but it's been quite a while since we saw a 6-mark question. So you need to know the expression for energy as it relates to amplitude, and then specifically energy is equal to half m omega squared times amplitude squared. You have to be able to find the difference in energy between two different times if oscillations are damped. And for simple harmonic motion, the total energy never changes. But for damped motion, the energy will change. And you have to be able to write down your thinking. So what was the amplitude at the different times? Write down the mathematics like I've done. Write the equation down algebraically and then put values in later. Specifically because if you do that and you make some mistake in your mathematics, if you don't have the underlying working in the underlying algebra, it's very easy for your answer to be assumed to be completely wrong. So always write down your thinking when solving a problem, not only if you're asked to explain. And so this was the last question. And you can see that these questions in oscillations dealt more with things like resonance and damping. And so I think we covered simple harmonic motion. I think we covered damping and everything in the topic of oscillations quite thoroughly. Check out my crash course if you think that you want to go back to some of the concepts to help you with these questions. If you find that these questions, if too many of these questions are too difficult to grasp, it is very likely that you may want to go back to the content itself, read, understand, conceptualize, get everything, digest everything and understand it well before you come to the problem solving. So maybe go back if you find these questions too difficult. Please like this video, comment, subscribe to the channel if you haven't already. Let me know if these videos are helpful. And if you need me to do any specific explanations or any specific videos, but I will be uploading more of these videos until I at least cover all of the topics for A-level physics in paper 4. And then maybe we'll move on to something like paper 5, which is desperately needed, I know. But for now, that's all from me, Mr. K. I'll see you again next time when everything is relative.